Hello, I am Radu Cristian, he's Mateo Robila and Mateo Mitraș, and we are students at Costache University National College of Iași, and we are going to present you a problem named bias.
Here are the contents of the presentation. In the pocket you have two coins, a fair one with a 50-50 chance of picking each side, and a biased coin having tail on both sides. We randomly choose a coin from the pocket and then toss it 3 times. We observed tail at each throw. The first point of the problem is, what are the chances to have picked the biased coin? And the second point of the problem is, suppose now that we can throw the chosen coin as many times as we want, and each time the result is a tail. Will we ever know for sure what coin we picked out? I'm going to start off with a brief history of probabilities. The scientific study of probability is a modern development of mathematics. Gambling shows that there has been an interest in quantifying the ideas of probability for millennia, but exact mathematical descriptions arose much later. There are reasons for the slow development of the mathematics of probability. Whereas games of chance provided the impetus for the mathematical study of probability, fundamental issues are still obscured by the superstitions of gamblers. The 16th century Italian polymath Girolamo Cardano demonstrated the efficacy of defining odds as the ratio of favorable to unfavorable outcomes, which implies that the probability of an event is given by the ratio of favorable outcomes to the total number of possible outcomes. Aside from the elementary work designed by Cardano, the doctrine of probabilities dates to the correspondence of Pierre de Fermat and Blaise Pascal, 1654, and Christian Huygens of 1657, which gave the earliest known scientific treatment of the subject. That's nice and all, but how do we use probabilities in everyday life? Probability theory is applied in everyday life in investment modeling, insurance and market, actuarial to pricing, trading decisions, government's ability in regulation, entitlements, financial regulation. Example of the use of probability theory in trading is the of the probability of spread mid-conflict prices, which will affect the economy as a whole. Assessment by a trader that are more likely than send that prices down signals traders of opinion. According to probability, neither independently nor necessarily rationally. The theory of behavioral finance emerged to describe the effect of such groupthink on pricing, on policy, and on conflict. In addition to financial assessment, probability can be used to analyze trends in biology, for example disease spread, as well as in ecology, for example the biological Punnett squares, which is a square diagram that is used to predict the genotypes of a particular cross or breeding experiment. As with finance, risk assessment can be used as a statistical tool to calculate the likelihood of undesirable events occurring, and can assist with implementing protocols to avoid encountering such circumstances. Probability is also used to design games of chance so that casinos can make a guaranteed profit, yet provide payouts to players that are frequent enough to encourage continued play. Now I'm going to define the simple rules of probability. For any event A, if P of A is the probability of event A occurring, we have the following. The probability of event A occurring is given by P of A, which is equal to N of A divided by N of S, where N of A is the number of elements in event A, or the favorable outcomes, and N of S is the number of elements in the sample space S, total possible outcomes. All probabilities lie in the interval 0 to 1, or 0 is less than or equal to P of A, which is less than or equal to 1. Total probability means the sum of the probabilities of all possible outcomes is equal to 1, or 100%. And the complement of event A, written as A prime, refers to everything that is not A, and P of A prime is 1 minus P of A.
The next part of the presentation we're going to talk about the definition of conditional probability. The probability that an event B occurs given the event A has already occurred is P of B on A, which equals P of the intersection of A and B divided by P of A. From which we also get that P of A and B intersected equals P of B on A multiplied by P of A, where the P of B on A is the probability of B given that A occurs, and P of the intersection of A and B is the probability of A and B occurring at the same time, and P of A is the probability of A occurring. And in the right part of the slide, we've got a representation of how conditional probability work. In the next part, we will use the probabilities of the diagrams, which represent all of the outcomes of an event, which is tossing a coin 3 times in our case. The given information is 2 coins, a regular one and a biased one, meaning that it has 2 tails instead of a head and a tail. If we pick a coin, then we throw it. The diagram will look like this. And in the right side, we have that the events in this tree diagram are F picking the fair coin, B picking the biased coin, and so on. Moving on, we know that P of F equals P of B, which is 50%, so we got an equal chance to pick either coin. And P of H given F equals P of T given F, which is 50%. So heads and tails are equally likely to land given we pick the fair coin. And P of H given B is 0%, and P of T given B is 100%. And so the biased coin will always land on tail, never on head. And using the rule of probabilities, which is P of the intersection of A and B, which equals P of B given A multiplied by P of A, we can work out that the probabilities of the final 4 outcomes, which is stated there. And the sum of the probabilities is 100%, as we see, which is expected. Now we will use the tree diagram for the events of picking a coin, then tossing it 3 times. The probability of the fair coin landing on tails all 3 times is P of T given F, which is the product of the probabilities of all the throws landing on tails, since they are independent of each other. And P of T given F is 50% multiplied by 50% multiplied by 50%, which is 1 divided by 8. And since the T is the complement of H and P of T given F, this equals 1 minus P of H given F, which is 7 divided by 8. And for the biased coin, the probabilities remain unchanged. And as we see, the sum of the probabilities is still 100%, which is good.
Now we are ready to answer the first question. What are the chances of having picked the biased coin, knowing that it landed on tails 3 times in a row? In other words, what is P of B given T? We know that P of B given A is P of A and B divided by P of A. So P of B given T is equal to P of T and B divided by P of T. P of T and B is equal to 1/2. P of T is equal to P of T and B plus P of T and F, which is equal to 1/2 plus 1/16, which equals 9/16. So P of B given T is equal to 1/2 divided by 9/16, which is 8/9, or 88.8 repeating percent. This is the answer to the first question. And here is the probability tree for all of the events and their outcomes. To answer the second question, for any number of throws or landing on tails, can we know for sure which coin we picked out? We modify the tree diagram for the events of picking a coin, then throwing it an n number of times. P of T and F becomes 1/2 times 1/2 to the power of n, which equals 1/2 to the n plus 1 power. P of T and B equals 1/2, it does not depend on n, and P of T becomes P of T and B plus P of T and F, which equals 1/2 plus 1/2 to the power n plus 1, which equals 2 to the nth power plus 1, over 2 to the power n plus 1. The end result is P of b given t equals P of t and b divided by P of t, which equals 2 to the nth power divided by 2 to the nth power plus 1. And 2 to the nth power divided by 2 to the nth power plus 1 is smaller than 1 for any natural number n. This means that for any natural number n, we can never know for sure which coin we picked out. But if n is really large, we can get really close to knowing for sure. If you take the limit of n approaching infinity of 2 to the nth power divided by 2 to the nth power plus 1, we get limit of n approaching infinity of 1 over 1 plus 1 divided by 2 to the nth power, which equals 1 over 1 plus 0, which equals 1. This means that as n gets larger...
So when you're saying the last 30 seconds, you mean the end result?
Yeah,
once again.
the end result, that's it.
Should I share my screen so I could show you the end result?
Can you, or can you switch on your camera?
But just one question before we get to the last slide. What about the rest of the video? Are you going to play the rest of the video?
No, it's already played. It was played on YouTube and streamed, but with the streaming, we had a problem at the end. So that was the time of the question, but we missed the last 30 seconds. So you can just...
No, it's just we were expecting for you to play the video while we were in this time slot. So yeah, it's just it's a bit unexpected. So excuse us for that.
Now my question was you to talk about it. Okay.
So we got at the end that the P for the B over T equals to 2 to the power of n divided by 2 to the power of n plus 1. We get that it has to be less than 1 for any n. And this means that for any natural number n, we can never know for sure which coin we picked out. So this is, and in the end, you can see the answer for the last question. So if the n is large, we can get really close to knowing for sure that the limit is 1 for the whole thing. And in the end, this means that as in n gets larger, we can get arbitrarily close to knowing 100% which coin we picked out. So this is the answer for the last question. If you want to see the answer for the first question, it's fine. Were you able?
Yeah, it's fine. We just missed.
I'm sorry, we cannot hear you anymore.
Oh, sorry.
Now we can hear you. Now it's back on.
Yeah, it's done. Thank you very much. We're now going to play a second video from the same school in Iași, and it's called Setting Arrangement.
Thank you.